Let's talk about increasing, decreasing, and monotonic sequences. A sequence AN is called increasing if AN is less than AN plus 1 for all n greater than or equal to 1. Okay, that's increasing. A sequence is called decreasing if the opposite occurs. So if AN is greater than AN plus 1 for all n greater than or equal to 1. And finally, a sequence is called monotonic if it is either strictly increasing or strictly decreasing. Okay, so I'm just going to highlight some of these terms to emphasize them. Increasing means, the next guy is bigger. Decreasing means the next guy is smaller. And monotonic means it's either strictly increasing or strictly decreasing. So there's two ways that you could show a sequence is increasing or decreasing. The first way is you show it algebraically. And this is basically a proof, like doing a proof. Okay. The other way that we can show a function is increasing or decreasing, or a sequence is increasing or decreasing, is we create a function, that agrees with our sequence, and we take a derivative. Now I want to show you an example of each of these in this video. So let's take a look at example 18 first. All right. So what do we want to do? We want to show it's decreasing. That means we need to show that AN is actually bigger than AN plus 1. All right. So what I'm going to do is I'm going to write down what is AN. Well, AN is just the general term. So that's going to be equal to 2 over n plus 3. And then I want to really compare it with AN plus 1. And AN plus 1 is obtained by basically writing our general term. But anywhere I saw n, I'm going to replace that with a n plus 1. So really, this is going to be n plus 1. I'm going to put that in parentheses, plus 3. Okay. And my goal is to show that this is, that the left side is bigger than the right side. So this is sort of, we're questioning whether that's true. Okay, so let's simplify this a little bit. The left-hand side is 2 over n plus 3. I'm going to leave that sort of questioning, is it really bigger symbol? And we'll have 2 over n plus 4. Now, at this stage, I feel that this is obviously true. Why do I say that? If you look at the numerators are the same. But if you look at the denominators, this side is bigger on the right. This denominator is bigger on the right, whereas this denominator is smaller. So anytime you have the same number in the numerator, but the denominator is smaller on one side, that means this whole fraction is going to be bigger, right? Just imagine if you had a pizza, if there were only 2 people, each of you get half a pizza. But if there's 3 people, each of you only get a third. So you get less pizza if you have a bigger denominator. All right. So That's pretty much good enough for me. So I'm going to take my eraser and I'm going to erase this question mark. And I'm just going to leave it like this. All right, let's take a look at showing that a function is decreasing by using the derivative. So let's take a look at example 19 together here. So what we want to do for example 19 is we want to create a function that's going to agree with our sequence for the different integers that we plug in. And the way that we do that is we are going to basically let f of x be equal to x over x squared plus 1. So I just want to mention that this, agrees with our sequence, since an is just going to be equal to f of n, which is n over n squared plus 1, right? So these n's are integers. Actually, they're really whole numbers, but so anyways, I want to show that this is decreasing. So I'm going to use calculus to do this. So I'm going to take the derivative of f. And the derivative of f, I need to use the quotient rule. So the derivative of the top function is 1. I want to keep the bottom, which is x squared plus 1. I subtract what I get when I take the derivative of the bottom, which is 2x. And then I keep the top function, which is x. And then I am going to divide by the bottom squared, which is x squared plus 1 quantity squared. So let me simplify this a little bit. This is going to be x squared plus 1 minus 2x squared, all divided by x squared plus 1 quantity squared. And this guy is equal to 1 minus x squared divided by x squared plus 1 squared. So when we look at this derivative, we want to look at the sign of this derivative. So let me rewrite it over here. So we had 1 minus x squared over x squared plus 1 quantity squared. I guess the first thing I'll mention is that the bottom is positive. When you look at the top will be negative for x greater than 1, right? Because you're going to have 1 minus x squared. The moment that x is bigger than 1, this term becomes bigger than 1. So this tells us that the derivative f prime of x is going to be less than 0 for x greater than 1, and this means that our original f is decreasing. F being decreasing, that means that our sequence an is also decreasing. Okay, so let's continue and talk about what it means for our sequence to be bounded above and bounded below. So a sequence is going to be bounded from above if there exists a capital M such that my sequence terms an are going to be less than or equal to m for all n greater than or equal to 1. So basically we're saying it's like m is like a ceiling. Our sequence an is called bounded from below if there exists a lowercase m such that an is actually, here, let me write it like this. I'll put m is less than or equal to an for all n greater than or equal to 1. So in this case, what I'm saying is that the lowercase m is what we call the floor. Okay, so if it's bounded from above, that means there's a ceiling to how big it can get. If it's bounded from below, that means there's a floor for how small it can get. A sequence that is both bounded from above and bounded from below is called a bounded sequence. All right, cool. So now we're ready to learn about the monotonic sequence theorem. The monotonic sequence theorem basically says every bounded monotonic sequence converges. So remember, we were talking about convergence of sequences. We learned about limits. We learned about squeeze theorem. Well, if you could show that your sequence was bounded and it was monotonic, meaning it's either strictly increasing or strictly decreasing, then your sequence is going to converge, which is nice. All right, everyone. We'll look at some examples in class. Take care.